Okay, this is related to a goodness of fit test, and we want to examine one of the greatest mysteries of our time, the distribution of colors in a package of M&Ms. According to Mars, the makers of M&Ms, the distribution of colors are as follows: 30% of brown, 20% of yellow, 20% of red, 30% of our other colors. Now, let's assume I bought several bags of M&Ms, and before, of course, I ate them all, I sorted them out because I'm OCD. All 200 M&Ms according to color, and found that 60 were brown, 50 were yellow, 45 were red, and 45 were other colors. Do the data provide sufficient evidence? We can do a test to conclude that the color distribution of M&Ms differs from that reported by Mars. Note, one categorical variable, i.e. color, different choices within that color variable representing our different groups, but one categorical variable, so we know that it is a goodness of fit test. Okay, so now we're able to solve this thing. And so we have step one, our HO and our HA. HO, probability of brown, we have 30%, so 0.3. Probability of yellow is 20%, so we have 0.2. Probability of red is 20%, so 0.2 as well. And probability of other 30%, 0.3. HA just simply does not follow the distribution specified in HO. Okay. Step two, as always, alpha is equal to 0.05, which is the appropriate level of significance mentioned in the question. Step three, this is where the fun begins. So we have our chi-square test statistic, right? Observed minus expected squared all over the expected value. Right? And we sum it up for every single observed item within this problem. Okay, so the first thing is we need to find the expected value of expected number of brown, expected number of yellow, expected number of red, and the expected number of others. Right? And that's just simply n, 200, times by the probability of a brown, which is 0.3, which gives us 60. Again, expected value of y is 200, times by 0.2, which is 40. And the expected number of red is the same as yellow, so 40. And expected number of others, 0.3 times by 200, again, 60. So with Excel, we have kind of a new way we can approach this particular problem. We can use Excel to do the calculation of that formula for us. So a couple of things we need to sort of keep track of. We need to keep track of what types of M&Ms that we had. So we had brown, we had yellow, we had red, and we had other. And there was two components to this process. We had what we observed, and we have what we expected. Right? Two key components of that particular chi-squared test statistic. So what did we observe? We observed 60 browns. We observed 50 yellows. We observed 45 reds. And we observed 45 of the other types. What did we expect? Well, we calculated the expected. We expected 60 of the brown. We expected 40 of the yellow. We expected 40 of the red, and we expected 60 of the other type. Okay, so we have a couple of choices at this point. We can use the formula to run through and do the calculations. Okay, and we saw that on the previous slides. Or we can use Excel in order to do some of the grunt calculations for us. We know the setup. It's up to us as statisticians to determine what's the appropriate test, what we're trying to evaluate, conclusions we draw, and the appropriate test statistic to use. It's perfectly fine to let Excel do the grunt calculator work for us. So if we recall, so we have our step 3, and that's just finding the test statistic. and we had step 4, where we find the p-value. Okay. And now we're going to just do it in a little different way, because Excel makes it easier actually for us to find the p-value and skip the test statistic step. Now I get it, the test statistic step, sometimes old school way. P-value is what we base the decision on. It's at the end of the world not to have the test statistic, and it's there for legacy a little bit, but some people like to have that test statistic so they can verify and things and so on. So we'll do both, even though I know we really only want the p-value. So equals 2, and chi test, very nice function. It's a function from the old Excel. Excel went and made it more complicated for unknown reasons. You'd have to ask them. So our chi test, and it specifies in the arguments there, actual range and expected range. So we highlighted the observed range, so a selection of values, comma, the expected range, all those expected values that we calculated, and then we close the bracket. Pushing enter, and we get our p-value of 0.076 approximately. Let's just copy that in there. Okay, so there's our function for that. Let's go back, find the test statistic, because we want to fill in that blank for step 3 in our test statistic. So we have a formula for that, and chi-inv is very nice in order to calculate that. Chi-inv asks for a probability. That's essentially our p-value. And then it asks for our degrees of freedom, which we found to be 3 from the previous step. And we push enter on that. And we got our test statistic of 6.875. Okay, so those are 2 functionalities. Not forgetting, of course, that our degrees of freedom is equal to 3. Okay, 4 different choices, -1. Step 5, we make our decision. All right. We do not reject HO as the p-value is greater than the alpha from this question. Again, with alpha okay, different alpha, we might have made a different conclusion. Okay, that's step 6. Now here's where it gets clunky. We sort of can conclude with so evident that it follows the distribution, but we say it kind of in a weird way, so we're not accepting HO. We lack sufficient evidence to state that the distribution of M's is different than that stated by Mars. Okay. So it's a little clunky because you want to try to avoid the best you can that anything that implies that you're accepting HO. And there you go. We're done. You'll notice that when you look at the questions worth 10 marks, it's because expected value and doing the chi-squared stuff takes a little bit of labor. And of course, I would always compensate you for that extra labor. Okay, thank you.